Hello everyone, welcome to today's webinar. Our topic is modeling of voice coil electrical parameters in EMS for SolidWorks. So we're gonna see today how you can use EMS and SolidWorks to model electromagnetic and electromechanical behavior and different phenomena that take place inside a voice coil. Our agenda for today is fairly simple. It looks like this. We're gonna, for those of you who are not very familiar with EMS, we're gonna go over EMS solvers and talk a little bit about different applications they have and what EMS in general can do for you. Then we're gonna get familiar with voice coils and how they function, what components do they include, and what sort of results what kind of simulation results we can get from EMS that will help us design and manufacture voice coils for different applications. After that, we're going to move actually into SolidWorks and EMS and see how one simulation of a voice coil actually looks like. We're going to wrap up this webinar by a short Q&A. However, if at any point during the presentation you have some questions, feel free to type them in the chat box and I'll do my best to answer them at the end. So, as I'm sure some of you know, EMS is a electromagnetic solver for SolidWorks. It includes a fairly large number of different modules, each of them specialized for different type of electromagnetic simulation. The main 6 modules can be grouped into 2 sets. The first one would be electric modules, which include electrostatic, electric conduction, and AC electric. And on the other hand, we have magnetic modules, such as magnetostatic, AC magnetic, and transient magnetic. Static modules allow you to analyze fields, inductances, capacitance matrices, torques, forces, etc. in static conditions where the field does not change, where you have certain maybe DC current or permanent magnet excitation, or in magnetic simulations, or in electrostatic you would have a certain charge, fixed constant charge distribution in your assembly, or fixed potential levels on different parts. So for these cases, you would use either electrostatic or magnetostatic solvers, and their main applications. The main applications of electrostatic solver include analysis of voltage breakdowns at high voltage insulators, the electric stability and integrity between winding layers, etc. Whereas magnetostatic solver is used for modeling of permanent magnets, permanent magnet machines, actuators, etc. Electric conduction is a unique module in the electric group, which is used mostly for analysis of electric current distributions in applications such as fuse design, direct resistance heating, and so on. And now we also have these AC modules, AC electric and AC magnetic. They are used for frequency domain analysis of electric or magnetic fields. By using them, you can see what kind of field plots, field results, impedances, forces and torques and losses you can get for specific frequencies of voltage or current expectation. They're used in AC magnetic module is used to study transformers, induction machines, inductors, chokes, all sorts of equipment where you have some AC high frequency excitation. AC electric module, on the other hand, is used mainly to model stuff like the electric losses or electric field distribution in assemblies where you have varying potentials. And finally, we have the most complex and most competent solver, which is transient magnetic, which allows you to do either steady state or sinusoidal or exponential pulse, any sort of excitation waveform that you can come up with. It can be used in transient magnetic solver as an excitation for your conductors, and it can come up with all the different results that I've mentioned. So it's the most general solver of all, and its applications include everything, pretty much everything I've mentioned so far on the magnetic side, in addition to motion studies where you have some induced voltages or non-sinusoidal excitations. So the most general cases would be covered by transient magnetic solver. In addition to these electromagnetic modules, EMS offers you also coupling to motion analysis, thermal analysis, and structural analysis. So, for example, you can take an electromagnetic assembly of different parts and analyze how does the field forces, so that the whole electromagnetic assembly of parameters, how does it change with certain speed of motion of specific part, or at the same time you can see how do the losses in the electromagnetic losses in different components, how do they manifest with the temperature distribution in the system, how does the temperature distribution in the system change depending on different electromagnetic conditions. Also, electromagnetic forces that get often developed in such devices, they result with some structural mechanical stress on your components. And you can use EMS structural coupling to compute these results. So now let's quickly get familiar with a voice coil, which is it's definitely a from a modeling standpoint. It is a complex device. First of all, let's do a brief overview of the basic components that come inside. In this case, a loudspeaker, which is the most common application, which is the most common device where you would find a voice coil. The loudspeaker basically, as a driving mechanism, includes permanent magnets and voice coil, but then it has some additional components like a spider and this loudspeaker cone, which are used to transmit the mechanical electromagnetic forces developed between permanent magnets and the voice coil into acoustic wave generated by the interaction between the cone and the air and the ambient. Why is it? The question one might ask is, why do loudspeakers use and why do voice coils use permanent magnets as a fixed component, whereas the voice coil is a component that moves? And the answer is quite simple. You simply have to keep the weight of the moving components very low to maintain high and quick responsiveness of your system with high frequency input signal. The audible range of human ear is at frequencies of up to 20 kilohertz. So to be able to generate these high frequencies accurately, you have to have the moving component cannot have high inertia, which would otherwise damp these high frequency signals, and that's why in voice coils the only thing that's moving is just this these few turns of copper wire, which is usually quite light, and that way the loudspeakers manage to maintain this responsiveness that is so important. But let's discuss briefly the overall modeling complexity of this system. As on the input side, you would have some power supply, some amplifier which would supply the current to the voice coil, and then in the voice coil, this electrical energy would generate some magnetic field, which will in turn interact with the field of permanent magnets and develop mechanical force. And this mechanical force will be transmitted to the cone, which will finally have some interaction with the surrounding air and generate the acoustic energy which we hear as a sound. So as you can see, there is quite a bit of energy conversion steps in this process, and the whole point of this webinar is to show how EMS can help us make these to make the bridges between different subsystems of this device. Although we won't be dealing exactly with the acoustic interactions, but we will show how EMS can help obtain characteristics of electrical side of the voice coil, as well as the electromagnetic side between which basically is characterization of the force developed between the voice coils and the magnets. So, as I have already mentioned, this is you can basically see what I just talked about in this simple diagram. On one end, we have varying AC current, which provides the current supply to the voice coil. But on the other side, we have mechanical system, which is formed out of cone and the spider. So our whole goal is to use EMS to compute magnetic forces for a variety of coil displacements and current magnitudes as well, so that later on we can take these results and plug them in a mechanical simulation to predict overall dynamic behavior of the whole system. So this is the way you would use EMS if you wanted to simulate the whole system. This is the way how EMS would help you bridge different subdomains. And at the same time, from the electrical side, from the circuit side of things, EMS will show how you can use EMS to compute the coil impedance for a range of coil positions and excitation frequencies, and see how for each frequency the impedance, inductance, and resistance of the coil are changing. So to do that, let's move right into SolidWorks, where we have prepared a small assembly of a loudspeaker. But the main, as you can see, we have the cone and the frame of it included. But the main components are actually the permanent magnets, which is this ring right here, and the voice coil. So the interaction between magnetic fields between the permanent magnet and the voice coil is executed by means of this iron back iron frame, which is a magnetic circuit which helps magnetic interaction between the permanent magnets and the voice coil. since our goal is to simulate behavior of the system for different coil positions, we're going to take advantage of EMS parameterization feature and take this distance between the voice coil and the base of the magnetic circuit and make it available to EMS as a parameterization parameter. So therefore, by doing this, EMS will now have access to this SolidWorks assembly dimension, which it can freely change as we wish, and generate simulation results for each position of the voice coil. So now let's move to the EMS Manager tab, where we have prepared modeling two simulation scenarios. One of them is magnetostatics case, where we have changed the position of the voice coil and obtained field and force results for each displacement. And we also have an AC magnetic study where we have done the frequency sweep of the voice coil impedance and generated the impedance profile for this range of frequencies. So the first thing in each EMS simulation would be to define material for each part. If you want to get accurate field results, it's important to use a nonlinear material, which is what we have used in this case. M27 is the material used for the core in this case, which can be found in the material library under the nonlinear materials folder. And here actually we can also see the pH curve of this material. Otherwise, the field results, if you use linear materials, field results might not be accurate enough. For permanent magnets, we have used neodymium magnets with coercivity direction defined along the Y, which is the Y-axis, the vertical axis in this case. The rest of the parts do not really participate in this simulation, as they are defined out of some non-magnetic materials. So the next step in defining this study would be to define the entry and exit ports for the current in this voice coil, which we have done by selecting the cross-section face of the voice coil, and to define the wire thickness, the number of turns, and the current magnitude. To make sure that EMS actually does compute the forces acting on this voice coil part, you simply right-click on the forces and torques folder in the EMS manager tree and select either virtual work or Lorentz force. In this case, it's better to use the Lorentz force, as its results do not depend on the fineness of the mesh on the faces of the part, which is the case in the virtual work method. So therefore, in cases where we have some current carrying conductors, it is better to use the Lorentz force method, as its results are not as susceptible to mesh distortion as in the virtual work case, where you really have to pay attention to the mesh quality on the specific part. Since most of the electromagnetic interaction takes place between the magnets and the voice coil, we have also defined a mesh control on these parts by specifying the maximum element size for the mesh. So therefore, EMS is going to apply a finer mesh on these parts, which are really important and really contribute to this analysis. So now let's see how we have defined these parameterization cases. As you can see, the distance between the voice coil and the base of the magnetic circuit is available in EMS as a parameterization parameterization element. So all we need to do is define the starting point, the starting distance from which we want to start this sweep, and the final point at which we want to end. The number of steps is going to be defined by the step size. So the smaller the step size, the more the finer the transition between steps will be. In this case, we have 11 scenarios between 5 and 11 millimeters of the voice coil displacement. In the results folder, you can generate few different field plots, of course, such as the B field, H field plots, current density plots, as well as the force density plots. Flux density plot and magnetic flux density plots would simply be generated by right-clicking on the folder name and then selecting the specific plot type that we want to create. So in this case, it might be interesting to see the fringe plot, which is basically the color plot of the B field. This plot actually does not tell us much, as most of the magnetic field interaction takes place on the interior of this of the parts that we see. So to cut it in half, we're going to right-click on this plot and select clipping, and then section clipping. And then EMS is going to cut this along one SolidWorks plane, and we can see the magnetic field density inside the assembly. Of course, we can also choose the scenario that we want to plot. So for this specific position of the voice coil, the maximum field density is about 2.4 Tesla. So we can easily tell that this core central portion of the core is quite saturated. If you want to see how does the field change with voice coil position, you will simply go to animate and then animate versus scenario. Then EMS will move this voice coil for us, and we'll see how does the field change. It doesn't change actually that much, but what is most important in this case is to get the force change with the voice coil position. And to see that, we'll go to the results table, and in the forces tab, we'll select FY, force along the Y direction, add it, and do the plot preview. And you can see the change, and it's quite a significant change in the force developed between the voice coil and permanent magnets for different voice coil positions. So there is clearly this force cannot be it would be quite inaccurate to consider it as a constant force for different displacements in the overall simulation. So definitely, this is a very important result without which we, our overall simulation of the loudspeaker would definitely suffer inaccuracy. So now let's move to the AC magnetic study, where we have pretty much the same materials. We have the same coil. However, this time the parametrization sweep has been done over a range of frequency. As you can see, we have started from 100 Hertz and went all the way to 2 kilohertz with a step of 200 Hertz. Therefore, we have again about 10 scenarios. For each of those, we can again have a look at the flux density plots. That's pretty much the same as what we had in the magnetostatic simulation. However, in this case, since we have some AC current as an excitation in the voice coil, we can also see what are the eddy currents generated in the core, because now the core is going to experience some changing magnetic field from the voice coil, and this magnetic field is going to induce some eddy currents in the core. What we can do is animate this eddy currents plot for a range of phase angles inside one period of the excitation frequency. What is obvious is that these eddy currents will definitely generate some extra losses, and definitely these losses will be higher at higher frequencies. So EMS is in the results table. We can also find the loss, the solid loss results, and let's see how do they change in the core for different frequencies. You can see how it's ramping up. The frequency is definitely influencing a lot these losses due to the eddy currents in the core, which is another very important result in the loudspeaker design, because the current magnitude and the overall power delivered to the voice coil is directly limited by the losses that you can tolerate and by the temperature that you can tolerate to have in your voice coil. So this is another important interaction, this electromagnetic to thermal, that EMS can also help you characterize, especially if we couple this simulation with EMS thermal. We would have been able to get also the thermal results for this loudspeaker as well. But before we finish with this results table, let's actually have a look at the impedance results. So let's add, as this is a complex impedance, we can choose either to have a look at its real part or imaginary part of the overall magnitude. But let's have a look at the magnitude of it. Same thing as expected. The higher frequency of the input current is definitely going to result, as we've seen, with the higher losses in the core, and these losses were going to be manifested as an increase and as an equivalent increase of the resistance in the coil, which is sort of a fictive resistance. It's not a DC resistance, but it's definitely opposing something that opposes that's something definitely that needs to be compensated as if it were an actual DC resistance. So EMS is able to give you these parameters about the coil impedance, which will help you design the amplifier and tell you how much power and what kind of current magnitudes and what kind of voltage levels you need to provide to be able to have certain currents and forces acting on your voice coil for a range of frequencies. So with these results, I would actually like to conclude let's go back. So what we have just seen is two EMS solvers complementing each other and allowing us to bring different subdomains of a complex electromagnetic device together and help bridge different physics and help bridge different phenomena for an overall system simulation. We have also seen how parameterization can help us use the resources we have more efficiently, to how it can help us take advantage of the fact that we work inside SolidWorks, which is the most powerful CAD package out there, and change the SolidWorks dimensions. It can be either angle or a distance, doesn't matter. We can use it through EMS parameterization. Also, I would like to invite you to check out some more similar examples on our YouTube channel or in one of our application notes on our website. If you would like to know more about EMS and different results it can provide and how it can help you in your simulation applications, please contact us through, at this email address or give us a call at this phone number. If you have some questions, now would be the right time to ask it. Now there is one question about the fill factor for the coil. Definitely the fill factor of the coil is automatically computed, and if it exceeds the maximum value, which theoretically is 1, but in reality is much less, EMS is going to warn you about it and might even prevent you from running the simulation. To define the stroke, yes, there is a question if you need to have a motion. I suppose it's you need to have coupling to SolidWorks motion to be able to define the stroke of the voice coil, and the answer is no. I mean, if it's a static case where you just want to analyze behavior at different displacements for a fixed frequency by using AC magnetic, you actually don't need to have a coupling to SolidWorks motion. You can just use parameterization and move and put the coil into different displacements. There is also a question with, but before I move to the next question, let me tell you that if you wanted to have even more general simulation scenario where you would analyze in addition to AC to sinusoidal excitation at the voice coil, you would also want to see what is the effect of the induced voltage in the voice coil that comes from the motion itself, and how does that in fact impact the overall behavior of the system. Then yes, you would have to use coupling to SolidWorks motion. Coupling to SolidWorks motion is mostly be useful for computing the induced voltage for different speeds, for different speeds of the voice coil, and definitely for the higher the speed of a voice coil, the higher the frequency of motion, the higher the induced voltage would be, and that would also have big implications on the amplifier design or the amplifier that you need to use in your device. There is also a question of whether we can do frequency versus displacement. Yes, definitely. You can generate few parameterization scenarios where you would either vary frequency or displacement and generate a full map of results. It would probably be some sort of a three-dimensional result space where on one axis you would have frequency, on second axis you would have displacement, and finally you would have I don't know, any results that you want to analyze over this two-dimensional solution space, such as maybe losses or force, anything like that. So if there are no more questions at the moment, I would like you to thank you for attending this webinar, and invite you to join us on the next time when we have a webinar, which will probably be in about 2 weeks. Thank you once again, and have a nice day. Bye bye.